variation and problem solving. All right. Well, this is something you're familiar with. We've talked in previous courses about direct variation and inverse variation. We're going to talk about that today. Direct variation, of course, is when one thing increases, so does the other. We're going to talk about inverse variation, and in that case, as one thing increases, the other decreases. Inverse variation. We'll start by going back to what we'd done in our last class. We're going to be solving for a variable. We're going to write an equivalent equation, but it's going to be n expressed in terms of a and m. Maybe I should use a highlighter here to just focus ourselves on the piece that we're most interested in. All right, so I want to have n all by itself. Remember, when we are doing these, we work in opposite order to order of operations. So let's see. This is being divided by a, so we want to multiply by a. M times a will equal 1 plus n. Now, this has a 1 being added to it. I could write it this way. N plus 1, commutative property. I want it all by itself. I want n all by itself. What do I have to do? Simply subtract 1 from both sides. This one looks nice. Right? There it is. Now I have re-expressed this equation in an equivalent equation, which is solved for n. This one asked me to do it for v. This is tricky because I have v here and I have v here. Oh my goodness. Oh my goodness. I'm going to have to do something rather tricky, I think, because I want to get v all by itself. Okay, so u equals v w. Well, maybe an interim step I could take would be to multiply both sides by v minus w. It seems like that might not be the right way to go, because now I'm getting, oh, please stop that. Now I'm getting the v on both sides. But I'll do it anyway. Now I'll have uv minus uw equals vw. I want all my v's on one side and everything else on the other. So I'm going to add uw to both sides. uv equals vw plus uw. But remembering that I'm solving for v, well, I've got v all over the place. I want to get it consolidated here. I haven't been successful at that yet. I want to get my v over here. So I'm going to say, all right, I'm going to subtract vw from both sides. So I have uv minus vw equals uw. So v and v. Oh! Does that give us a clue what to do? Gives me a clue what to do. I want to factor out that v. Now I'm in very good shape to solve for v. V is equal to uw divided by u minus w. Very sweet. All right, so I finally got my v isolated. Then I divided by this factor, and there it is. Direct variation. If the ratio is constant, then y varies directly with x. As x increases, y increases also, and k remains constant. Or I could look at it this way: as y increases, x increases, and the amount x increases is controlled by this constant. Here are some examples of direct variation. F equals ma. So as f increases, m increases. As f increases, a increases. What would be my constant of variation? I guess I don't know right now, but it looks like it's 1. Does m vary directly as f? Let's see. As m goes up, what has to happen to this side? That has to go up also. So the answer is yes. Does m vary as a? Well, if this goes up, if we're going to stay true, what has to happen to a? That has to go down. So we'd say no. Otherwise, our equation would not stay true. Here's a really good example. The length of a spring. All right, so we've got a spring, and it's got some weight on the end of it. And we're going to think of this as the force. The length of the spring varies directly as the force applied to it. When the spring is stretched 4 inches, so we've got 4 inches here. The force is equal to 8 pounds. Find the constant of variation in the equation. All right. So I would say the length of a spring, L, where it says varies directly, I'm going to say equal to some constant of variation times whatever is here. In this case, it's force. And I've said I'm going to make that a capital F. So I've got my basic relationship written down. I'm trying to solve for K. This is my constant of variation. All right, so I've got some numbers. If I didn't have some numbers, I could never figure this out. I have 4 and 8. I can plug those in. Length of a spring when it is 4 inches, still equal to some constant of variation, which I'm about to figure out, times 8. It's pretty simple for me to figure this out. I'm just going to divide both sides by 8, so my K is equal to 4 divided by 8, or 1/2. I am not done. I need to find the equation of variation. Now this is the basic equation that's true for this situation. It's L equals my constant of variation times the force. My constant of variation is right here. Now you're done. A lot of students will do these two pieces and quit. Don't quit there. Make sure you write out what the equation is. Otherwise, you will not get full credit. We're going to talk about inverse variation. If the product of x and y. So now we're talking about the product, where previously we were talking about the ratio. See, we had a ratio of x and y. Now with inverse, we're talking about the product, x times y. With this, if that product is constant, here's our k for constant, then as y goes up, x must be going down, true? Otherwise this wouldn't be constant. Or we could look at it this way, as y goes up, x goes down. Let's look at this one. Does P vary inversely with Q? Well, assuming now that T isn't changing, if P is going up, what is going to happen to Q? Well, it's going to go up also, isn't it? So, no. Let's try another one. Does P vary inversely with T? As P goes up, assuming Q can't change, T would have to go up also. So no. We'll try another one. Yeah, I'm getting discouraged. We can't find inverse variation here. Does Q vary inversely with T? Let's see. Well, assuming P isn't changing, as Q goes up, we can't have T going up because this side would be getting smaller, so T has to be going down. The answer here is yes. Finally, we have an inverse relationship. And I can prove it to you using this definition here. We can write an equivalent equation, and we'll say P equals QT. And you can see that we're talking about the product of those two variables staying constant. That would be inverse variation. We have great examples of this in electricity. The voltage V in an electrical current varies inversely. So when you see this varies inversely, you're going to put your K in here. And underneath it, because it's inverse, you're going to put whatever it is that's varying inversely with it. All right, so the voltage in the circuit, so we have at least one point here where the voltage is 12 volts. When the resistance is 240 ohms. Find the equation of variation. Well, to find that, we first need to find our constant of variation, which we are going to be able to do because we have been given a couple values. We can say 12 is equal to K over 240. Our K will be 12 times 240. Oh my goodness, what is 12 times 240? Let me think about this a minute. 12 times 120 would be this, and I'd still have 2 to worry about, so my K must be that. Ooh, big K. Right, so I found K. That's what my K is equal to. But remember, we're being asked to find the equation of variation. So we're going to go back here only now we know what K is. So we can say the equation of variation is voltage equals 2880 divided by whatever the resistance is in ohms. All right, let's look at this one. The cost of lighting a 100 watt light bulb, and of course we do this in cents because electricity, despite all our concerns about the cost of electricity, when we're talking about just doing a light bulb, we better talk in cents. The cost C of lighting a 100 watt light bulb varies directly. When I see these words, varies directly, that's when I write equals K times, in this case, T, the time. The cost of using the light for 1,000 hours okay, so the time is 1,000 hours, and the cost is 15 cents. Write the equation of variation. Equation of variation. All right. Well, the very first thing I have to figure out is, what is my constant? I have at least one set of values so I can figure out what my constant is. 15 cents equals K times 1,000. So my K is 15 over 1,000. We might also write it as a decimal, right? I move my decimal place 3 places. So I'd have 0.015. Two different ways I could write it, as a fraction or as a decimal. Now I was asked to put together the equation of variation, so I best do that. C equals 0.015 times the time. There's my equation of variation. Now that was the first thing I was asked to do. The second thing we haven't talked about. Determine the cost of using the light for 2,400 hours. This seems pretty straightforward. The cost will be my constant of variation times my number of hours and you get your calculator out and you will find that that is equal to 36 cents. Let's do another one. The time required to harvest the potato crop varies inversely. Oh, okay, so this is going to be a little different. I'm going to say T. Remember when we see those two words, varies inversely? We set it up like this. And what it varies inversely with is going to go into the denominator. The number of people on the job. Well, that makes sense. As we increase the number of people doing the job, the time to do the job will go down. An inverse relationship. It takes 8 hours, so we're looking at time in hours, for 10 people, so a number of people equals 10, to do the job. Now we're not asked here, you don't see it anywhere, that it asks us to create the equation of variation. However, we know we need it. So the very first thing we're going to do is figure out what that equation is. Then we will answer the question that we have here. So our equation requires us to figure out what the constant of variation is. We've got an 8, we've got a 10, so we can say 8 hours equals our constant of variation, which we don't know yet, divided by 10. Our constant of variation turns out to be 80. So that means our equation is t equals, the time equals 80 divided by the number of people. That's our equation. Now we'll go to part 2. Part 2 was how long will it take for 36 people? So when n equals 36, what will the time be? It'll be our constant of variation divided by 36. You get your calculator out, please. Two and 2/9 hours, which we could convert 2/9 into minutes, couldn't we? We did, I think we did that earlier. Let me do a fancy pen. Done. It's always sweet to see that come up, isn't it? Okay, you've got some problems to do back in class. I'll see you there.